Continuing on with our gas laws, we want to mention one additional gas law. Keep in mind we've talked about several already. For example, we've talked about the combined gas law. And from the combined gas law, you can get several gas laws. For example, Boyle's law, Charles' law, Amonton's law. We talked about the law of Dalton's law of partial pressure. And we also talked about collecting gases over water. We mentioned Graham's law of effusion. That's what we just covered, where the velocity of gas A over the velocity of gas B is inversely proportional to the square root of the molar mass of gas B over the molar mass of gas A. And today what we're going to look at is Avogadro's principle. And Avogadro's principle shows the relationship between the volume and the quantity of a gas in moles. Joseph Gay-Lussac talked about the law of combining volumes. It says gases react in volume proportions that are whole numbers, provided that conditions are held constant, such as pressure and temperature. For example, if you're looking at the synthesis of hydrogen chloride gas from hydrogen and chlorine, instead of talking about mole ratios, you can talk about volume ratios when you have gases. That is, one volume unit of hydrogen, in this case let's say liters, reacts with 1 liter of chlorine gas to generate 2 liters of hydrogen chloride gas. So the volumes are determined from the coefficients, and you can be in liters or mils, just be consistent. We can then generate volume ratios to do simple conversions. For example, it says if 2 liters of hydrogen gas react with an excess of chlorine gas, what volume of hydrogen chloride should be generated? So if we look at this equation here, we have hydrogen gas and chlorine gas, and again, you've got to have gases to do these volume proportions, generating 2 moles of hydrogen chloride gas. If we're given 2 liters of hydrogen gas and it reacts with an excess of chlorine gas, hydrogen then is the limiting reagent and you have 2 liters of it, we can figure out what volume of hydrogen chloride gas should be generated. And instead of doing a mole ratio here, we'll do what's known as a volume ratio, and it is determined the same way as a mole ratio, just the units will be different. From the balanced equation, we have 1 liter of hydrogen gas to 2 liters of hydrogen chloride gas. 2 times 2 is 4 liters of hydrogen chloride. And some of you probably can do this in your head without writing it all out. For example, if you had 3 liters of hydrogen gas, you should be able to generate 6 liters of hydrogen chloride gas. Or if you generated, for example, 10 liters of hydrogen chloride gas, you must have started with 5 liters of hydrogen gas, provided that the chlorine was in excess. So this is a volume ratio, and we'll come back to this a little later on in the unit. Our other focus is known as Avogadro's principle. And Avogadro's principle says that equal volumes of gases at constant temperature and pressure contain equal numbers of particles. You've got a direct relationship between volume and moles of gas. And again, whenever you divide 2 variables, they are directly related, dividing them on the same side of the equation set equal to some constant. So here is Avogadro's principle, where our volume over moles under the first set of conditions is equal to the volume over the moles under the second set of conditions. And again, just as we talked about with Charles' law and Amonton's law, you can see the direct relationship between volume and the number of moles. One other thing I want to remind you of before we do 4 simple problems. At STP, 1 mole of any gas occupies 22.4 liters of space. This is known as molar volume, and that constant is provided to you on the back of your periodic table. Again, for second semester, you've got molar volume at STP, that's standard temperature and pressure. Temperature is 0 degrees Celsius and pressure is 1 atmosphere. Molar volume, 1 mole of any gas occupies a volume of 22.4 liters. So molar volume is 22.414 liters per mole. And this can become an equality that you use as well. If you have 1 mole of gas, you have 22.4 liters. If you have 2 moles of gas, you have 44.8 liters. 3 moles of gas, you would multiply this by 3. If you had half a mole of gas, then you'd have 11.2 liters. And you'll see some of that here. And again, molar volume is given for you. I've reiterated standard temperature and pressure at 0 degrees Celsius and 1 atmosphere of pressure. In the first example, here's where you're using Avogadro's principle. You have 6 moles of gas occupying 3 liters. If the volume is decreased to 1.5 liters of space, you want to know how many moles of gas are present. Now this one most of you can do in your head. You're going from 3 liters to 1.5 liters, so you're decreasing by a factor of 2 or dividing by 2. So all you would need to do is divide 6 moles by 2 is 3 moles. Alternatively, you can work through the problem as such. You've got N is equal to 6 moles. You've got a volume equal to 3 liters. You've got a V2 of 1.50 liters, looking for N2. Avogadro's principle says V1 over N1 is equal to V2 over N2. Do a double reciprocal because you don't want to solve for something in the denominator. You're more apt to make a mistake. Variable manipulation you are strong at. You've got V2 is 1.50 liters, N1 is 6 moles over 3 liters, and again half of 3 is 3 moles, as we said previously. Very straightforward. Don't foresee any issue there. Number 2 involves what we talked about, where 1 mole of any gas at STP occupies 22.4 liters. So if you have 2 moles of argon at STP, what volume would that occupy? And again, you know that 1 mole of any gas occupies 22.4 liters of space. So 2 moles then of argon, and you must be at STP, will occupy twice that, or 44.8 liters. And it doesn't matter if you have argon, helium, neon, carbon dioxide, etc. 2 moles of any gas will occupy twice this volume, or 44.8. Let's link back to some simple stoichiometry that we talked about previously. In number 3, it says, what volume does 20 grams of krypton occupy at STP? So we have 20 grams of krypton, and we want to know the volume at STP. Well, we know 1 mole of any gas at STP occupies 22.4 liters. So the first thing I need to do is convert this to moles using the periodic table. This is something you learned back in chapter 7 from the periodic table. And here's the new piece. 1 mole of any gas at STP occupies 22.4 liters. So you've got 20 times 22.4 divided by 83.8, and that's going to be 5.35 liters. So take a minute now to do number 4. This one's a little tricky. Be careful of nitrogen gas. Remember what I said, there's 5 diatomic gases. And take a minute now to try and do number 4. And let's take a look here. On number 4, we've got 40 grams of nitrogen gas. Don't forget nitrogen's diatomic. 1 mole of any gas is equal to 22.4 liters of space at STP, and you get 32.0 liters of nitrogen gas. So in regard to Avogadro's principle, on classwork 3.2b, that would be number 17. But for your next class, you want to make sure that you've done these problems specified, because that will allow you to master both Dalton's law with the combined gas law, Graham's law of diffusion, and now Avogadro's principle. So this is an additional gas law that we need to master. There are many in this chapter, and we can make a list of them next time to make sure you understand the ones we've done, as well as the ones that we will be exploring.